We're now going to look at an example of how a neural network with nonlinear activation functions fits a curve to the data. So networks do much more than fit straight lines, and it's these nonlinear activation functions that allow us to draw arbitrarily complex divisions in input space to distinguish among our inputs. The activation function shown on the bottom left we've met already. It's the logistic function. It's bounded by 0 below and 1 above. And for an input of 0, net input of 0, it produces an output of 0.5. Another one that is not as popular, but I like it, is the hyperbolic tangent function, or tanh function. It's shown on the right-hand side, and you can see it's basically the same thing. It's an S-shaped function, but the bounds are different. This is bounded between -1 and +1, and an input of 0, a net input of 0 to this unit produces an output of 0. So depending on the characteristics of our data, there may be reasons to choose one or the other. There's the underlying math for these activation functions, but we don't have to worry about that because we've got scientific calculators and computers to do all the calculation for us. From our point of view, we need to know that these are sigmoidal functions, bounded above and below, and to be aware that there's no point in asking a unit with a logistic activation function to produce a negative output, for example. In both cases, they are sensitive, maximally sensitive to variation in the input when the input is centered around 0. And they differ really only in their bounds. So what happens when we use a nonlinear activation function on the simple networks that we've been looking at? Well, instead of fitting a straight line, as a linear unit does, these fit S-shaped curves to the data. So we're just fitting a different kind of curve. And by combining multiple output units, we can make arbitrarily complex divisions in the input space. We're going to see an example that should make this clear. First, though, a little revision from the first lab. Here's a neural network with a single hidden unit, a linear output unit, a single input, and a bias on the hidden and the output units. And the unit numbers, which are necessary to describe the weights, are given there. The bias is 0, the input is 1, the hidden is 2, and the output is 3. So we want to write an expression for the function computed by this network. And we're going to assume that that hidden unit has the tanh activation function. The underlying maths is messier, but when you're writing things symbolically, tanh is really easy to write. So let's start. Let the input be x. And let's consider first what the hidden unit computes. So the hidden unit is a tanh unit. So it's going to compute the tanh of its net input. And its net input is the weight to unit 2 from unit 1 multiplied by the input, plus the bias term, which is the weight from unit 0 to unit 2. Now the output unit receives input from the hidden unit and from a bias. It's a linear unit, so we don't have to worry about activation functions. So it's the weight to unit 3 from unit 2 times the activation of the hidden unit, plus its bias term. And put it all together, that's the function computed by this network. And what that is a single S-shaped function. If we were to use this instead of the straight line regression that we did earlier, we would obtain a slightly better fit to these data. So looking at these data now, we might begin to question whether it was really a good idea to fit a straight line in the first place, when the relationship that the data speak of looks curvilinear. So, in fact, when we fit the data using an S-shaped curve like this, we actually obtain a somewhat better model. That's the example we saw before. Now let's consider a slightly more complex data set. Here's a data set again. I'm afraid they come from automobile data, and I'm not too sure they have something to do with emissions. Doesn't matter. Look at that scatter plot. It's got a big bump in the middle. these are highly nonlinear data. There's no point in trying to fit a straight line to these. If you were to try to, you would end up with a straight line, a horizontal straight line that would be of no use as a model for these data. Rather, what we're going to do is we're going to use a network shown here on the right-hand side, in which there are two hidden units and one linear output unit. The two hidden units each provide a different S-shaped curve, so that the output unit will be the sum of the two S-shaped curves plus an offset, the bias. And what I'm going to show you is the output from the S-shaped curve associated with each of the two hidden units, that's tan H1 and tan H2 there, and the output unit. And here you can see they're just random because this is before training and I've just given the network random weights. So it's not doing anything great at this stage, but we're going to follow these three curves as we step through the data, updating the weights each time. We'll see the mechanics of backpropagation later, but we want to know what it's doing underlying. So after 8 passes through our data set, what we can see is that functions have changed, but not a great deal. You can see the output, which combines the tan H1 and the tan H2 and an offset, is elevated. It's got a little bit of a bump in it, but it's still not a good model. That's after 8 passes through the data. After 12 passes through the data, now you can see that the two tan H functions have taken on very different and contrasting shapes. Tan H1 starts low and goes high. Tan H2 starts high and goes low. The output, which adds these two together, now acquires a bump in the middle. This is looking more promising. After 20 epochs then, that's 20 times through our data set, the output is as good as it's going to get. And it has actually done a fantastic job of fitting the data, despite the fact that the data is so highly nonlinear. It turns out that this particular data set can be well modeled as the superposition of two tan H functions. That was one run through a training of this network from a random starting position. Now we could try it again, and we would begin by choosing a different set of random weights, and our path to the trained model would then be slightly different. So here's a plot showing you 4 runs, each time starting with a virgin network in which we just choose random weights, but there are different random weights for each of the 4. The x-axis here shows the epoch number, so that's each epoch is one pass through our training set, after which we update the weights slightly. And the y-axis here is the overall error on the training set. And what you can see is that although all 4 training runs begin more or less at the same place, slight differences because we're choosing slightly different random numbers, but they're all lousy. They all end up at the same place. They all find the same solution. For a more complex problem, that might not be the case, but in this case, they all find the same solution. But they take very different lengths of time to get there. On one run, we're as good as we're going to get after 10 epochs, whereas on another one, it takes us 30 epochs to get there. And this is entirely typical. What we'll find when you're training networks is that successfully training a network is not enough. You need to demonstrate that you can do it again and again and again. It is always possible that your initial choice of weights was serendipitous and just happened to work, and we need to guard against that. We just used 2 tan H units to fit some highly nonlinear data. And we've seen straight line fits. We've noted that the logistic function and the tan H function both provide us with S-shaped activation functions. And this doesn't exhaust the possibilities of activation functions. All kinds of activation functions have been tried out. And now and again, some new activation function comes into vogue in a specific architecture. In the 80s and 90s, which is the period we're most interested in this module, the vast majority of networks use the logistic function and the logistic function only. That's also the one we'll be using in basic prop because there's no need to make things more complicated when you're just learning. But when you're working on a specific problem, if you're in the field of neural networks, the more you understand about the problem, the better able you will be to choose an architecture and a training regime that suit the characteristics of the problem. S-shaped functions are highly generic. All we care about is the upper and lower bounds. But modern networks are exploring quite a few other activation functions. One that we've met already is the binary threshold unit. I shouldn't say neuron, it's units. These are the kind of activation function found in the perceptron. And indeed, these were derived from Warren McCullough's original observation that a spike in a neuron, it has this character of being all or nothing, of being there or not there. And he made the imaginative leap to associate those with individual bits. A closely related kind of activation function is the linear threshold unit, which basically stays quiet until its activation passes a threshold, but then it produces output proportionate to the excess of the input over the threshold. So this is a nonlinear function with a discontinuity at the threshold. There's our friend the sigmoidal function. This is a smooth, continuous function. Unlike the last two, this does not have a discontinuity. That turns out to be the key to unlocking back propagation and moving beyond the dead end of the perceptron. The fact that this is a smooth, continuously differentiable function, that means we can describe its rate of change at every point, allows us to use basic calculus in setting the weights, as we'll see in the next video. The tan H function is pretty much the same. There are many others.